Okay, so good morning, everyone. We'll continue with lecture 27. And last time we were doing a mixed random variable, and we know that mixed random variables are random variables that have continuous part and the discrete part. Okay, so it's neither fully continuous nor fully discrete. And recall that the random variable is called fully continuous. It's called continuous if the CDF of the random variable is continuous, and it's called discrete if the discrete function is of the staircase form. Okay, so it's like it has jumps at every discrete points in the domain. Okay, so that's when the CDF will look like staircase. So last time we were discussing this problem as an example of the mixed random variable, and we were given a continuous random variable with the following PDF, and we were given y as a function of x, and then we went ahead and found the CDF of y, and when we did that, we found that the CDF of y is neither it can't be classified as a continuous, and it can't be classified as a discrete either. So that was a motivation for us to introduce mixed random variable. And to recall everything in terms of picture, so this is what we saw. The CDF of y looks like this. So it has clearly a jump at half. Okay, y equals to half, and hence it's only continuous for y less than equal to half, and then after that y greater than half it's continuous, but there is a jump at y equals to half. So that's where there is a discontinuity. So it's not continuous and it's not a continuous random variable, and it's neither in a staircase form. So we declared that it's a mixed random variable. So in the previous example, what we saw is that CDF of y was this, right? So CDF of y was this. This is something we solved in the last class, okay? And that was the plot that I was showing for this, okay? And the CDF can be written as a sum of continuous and discrete part, okay? So that's what I'm claiming now. CDF can be written as a sum of continuous and discrete parts. Let us see how. So I can write this as continuous part and the discrete part, where the continuous part is written like this. Okay, so I can write the continuous part as like this, because to make it continuous at half, I have to make it 1/4. If we see the figure here at 1/4, right? So to extract a continuous part and to make it continuous, we have to make it like we have to make it like flat like this, right? So after this, okay. Okay, so it has to be like flat like this. So like after half, what we want is like it's 1/4 after this, right? So that could be extracted as a continuous part, and then the discrete part could be this guy. Okay, so it's like discrete part would be like the jump that we got, right? So jump will be like 3/4. Okay. Okay. So this is the continuous part, and the discrete part is the 3/4 part, right? So from half onwards, what was the jump that we got, right? So the discrete part took the remaining part that was left, and that's the discrete part. Okay, so it's from half, and then the less than half we are making it 0. Okay, deliberately. So we have written this, rewritten this in terms of continuous and discrete part. Okay, so the things where they break is the jump point, right? So this is the jump point. So that we recall, right? So this is where they break. And from there, like we can extract the discrete part. This is a simple case, but sometimes it may get complicated, right? We won't be doing too complicated things anyway in this course. Okay, so this is the case where we can actually differentiate, extract. So in general, what we get from here is like the CDF of mixed random variable can be written as the sum of continuous and the discrete or the staircase form, right? So this is the continuous and discrete part. And under PDF is given like this. Can we like back the PDF? And we know that for PDF we have to like differentiate, right? So can we like do that? So if we differentiate, then we can only differentiate the continuous part, right? So continuous part, if we differentiate, then we got a small c here, right? So small c y is dcy by dy. Okay. So and we are assuming that it's like differentiable moreover, okay? Because continuity does not necessarily mean differentiability, right? So although we may have extracted a continuous part, there is no guarantee it's differentiable. So we are making an additional assumption here. So additional assumption here, okay, for the continuous part to be differentiable as well. Then we can retrieve cy and let y1, y2, all those discrete points where we found the jumps, okay, for the discrete part. That is the points for which we had some kind of jump. In other words, the probability was non-zero. Okay, and then what we can verify is this. So remember that, so this is like the PMF of the discrete part, okay? PMF of discrete, and this is the PDF, right? Remember in continuous case, we talk about PDF, not PMF. So PDF of the continuous part, okay? So again, like as usual, we would verify, like if it was fully continuous, then we know that the PDF integrates to 1. And in the discrete case, the PMF, okay? So the PMF sums to 1, okay? So this was individual cases. And then in the mixed case, what we are expecting is something like this, okay? So all possible jump points there, and then plus the sum of the remaining continuous part, and then they should add up to 1, okay? So that's the mixed case. The expected value of y in the mixed variable case can also be, like as usual, extended like this. So the only thing to remember is like you have to know what is the PDF. Okay, so what is the PDF? Let us say you could differentiate it for the continuous part, and then you put a y here to get the expectation for the continuous, and then you have the PMF, and then you just put yk here, and that gives you the expectation. Basically, it's the expectation of the continuous part plus the expectation of the discrete part, okay? And that gives you the expectation of a mixed random variable. Okay, so in this example that we have seen so far, the only example of mixed random variable, can we check the validity of this argument? Okay, so can we, I mean this argument, okay? So validity of CDF, like PDF, okay? So that should integrate to 1. That's what we know should be true for any random variable. The PDF should integrate or sum to 1. So this is the situation we have in the example that we have seen so far. So Fy is Cy plus dy, and where the continuous part we know is this. This is something we derived in the last class. Okay, so this is in the last class. And discrete part is this, right? So that's 3/4/0. So from here onwards, I mean, okay, we should not look into this figure, right? So it's like you make it again, right? So at half, you get a 3/4. So this is your discrete case, okay? So I mean, so that's the like discrete part that is like separately done, and the continuous part separately would be like it's 0, and then from here it went up to half, and then this is half. So this is the continuous part, this is the discrete part. We have done this plot separately. Okay, this is bold because 1/4 is achieved here. Okay, so this is like 1/4 here. Okay, and what we want is now this. Okay, so this should like integrate, and then they should like sum to 1 basically, right? So so what does this mean here, right? So if I integrate cy, so if I integrate cy, then it's like from -infinity to infinity, right? So if we check this guy, So integrate minus infinity to infinity. Do I have a space here? No. Okay, so cy, this is minus infinity to infinity, and cy dy, look, below 0 there is nothing, right? So we can actually start from 0, and yeah, basically from, yeah, so basically from 0 to infinity, right? But the range of y beyond half is 0, right? So we have to do it between 0 and half only, right? Because we integrate this, remember, only up to the range, right? So it's like below 0 and 0 to half, basically half included, and beyond that is 0. And the function here in this case is y square, right? And y square dy. No, but I have to integrate what? Sorry, I have to integrate the PDF, not the CDF, right? Okay, so what was the oh, okay, we did not do the differentiation, right? Okay, we did not find the small c yet, right? Okay, so we have to differentiate the c here, right? Okay, so we differentiate c in this interval because that's the valid CDF region. So it's like 2y, right? So it's like 2y dy. So this is like 2 y square by 2 and 0 to half. So this is like 2 goes away. So this is like 1/4. Okay. So 1/4 plus 3/4. 3/4. Okay. Remember, discrete case, what is the valid range? The valid range in the discrete case tells you that, look, if this is flat after this half onwards, then this means that these guys, any other point or whatever value you're thinking of, you're treating this as discrete, right? So like after this is anyway flat, right? So the contribution of the CDF is 0, okay? So, okay, this is continuous case, I'm sorry, here. Okay, so at half it's like, I mean, including half, I mean, it's 3/4. And after that, like, it has to be like 0. That's why, like, there is no contribution beyond half. So these guys are 0 anyway, right? Okay, I mean, I'm plotting PDF, okay? Don't get confused here, right? So these are like PDF, PMF here, and this is like PDF, okay? So if I draw PDF, then it would be like 2y. So it's like this, I guess, 2y. So I have to find area under the PDF, right? And beyond that, there is no contribution. So like the PDF was flat anyway, right? So this was 0. Okay, it dropped suddenly, and this was 0. And in the PMF case, there was just one value there, and there was 0 here and 0 here. Okay, so that's why I just stop at 3/4, because in the discrete case, the range is the value for which the positive value is found, right? So the positive value is found only for the half, which is 3/4, and other cases it's 0, right? So that's why I stop at 3/4. That's the only place where this is found. And then in the continuous case also, I did integration from 0 to half only, because otherwise the values that the PDF takes is 0. Like if I differentiate this beyond this, then small c of y will be 0. And here also small c of y will be 0. And in this case, the c of y will be 2y. Okay, so c of y, okay, I should have done this step before, right? So y equal to half, and this is like 2y, 0 less than equal to y less than half, and this is 0 for y less than 0. So this is what we have used here. So this means that the range, remember, the range is defined where the positive value is taken for PDF. So this is the only value. So this is why I integrated from 0 to half only, and then 2y, and then this is what I got. Similarly, for the discrete case, the range of d y is just a half, because that's the only place where it's taking the positive value. After that, it's not augmenting at all. So I just do 3/4, and this is 1. Okay, so that's what we verified for the mixed case. Mixed case is a little bit one has to do figure out a little bit. I'm not going to do too much of discrete mixed in this case. This was just an example, and more or less I will stop here. So let us see, like, how do we compute the probability when we are given the discrete case? So this is a like example of the mixed random variable that we have already seen. And now the question is like, what are the probabilities that you're going to calculate? The only thing here is like you have to be sure that you're taking into account if there is any jump or anywhere, if there is any jump right somewhere, then you take that into account and probability that, yeah, so these are the probabilities that we are, and we have to compute the expectation of y, right? So like how do we like compute these values, right? So let us do this simple example of mixed random variable where we have to compute probability, and this is a mixed one, right? So the first question was probability that y is greater than equal to 1/4 and less than equal to 3/8, right? So I write this here, okay? So what we have to find is probability that 1/4 y and less than equal to 3/8, okay? And this is look the for y greater than this and less than equal to b, we had the formula, right? So where the only point that is left is 1/4, so we have to add back that, right? So this is like fy 3/8 minus fy 1/4, and then we have to add this fy 1/4. Okay, so what we want to recall? What we want to recall is probability that a less than x less than equal to b. This is the formula that we wrote before. This is fx b minus fx a. Okay, and there is equality here, so we added back this, and this is true. This is true for any type of random variable. Any type of random variable. It could be continuous, discrete, or mixed. Okay, so this can be like verified. So we are applying this in the mixed case. So we know that this up to here is the is probability that 1/4 less than y less than equal to 3/8, and we added back this because this point was left. Remember that in the case of mixed, we are a bit careful. We add back. Okay, so we add back in the case of discrete. But if it was a continuous case, we know that this guy, we have noted this down. Okay, so this guy is same as a less than equal to x less than equal to b. This guy is same as probability that a less than x less than b. This guy is same as probability that a less than equal to x less than b. Okay, so in the continuous case, in the continuous case, all these are equal, right? But in the discrete case, like all these are equal, then it means that I could have written all the time I will write like this. Okay, and no need to worry if it was continuous. But if it is a mixed case, then only this result is true. This may not be equal to this. Okay, so if x is mixed random variable, then probability that a less than x less than equal to b may not be equal to probability that a less than equal to x less than equal to b. Okay, so remember this guy, mixed. Okay, because it could be that there was a jump at this. Okay, I leave it up to you to verify, like, is it also true that like this guy may not be equal to this, or this guy may not be equal to this. I leave it up to you to find out which cases are not going to be equal. Okay, so in particular here, what I'm claiming is like, if there was indeed a jump at a, then it is risky to just keep this. You have to add back the a part here. Okay, so this is what we have done here. We add back because it is discrete, because x or y is discrete random variable. Okay, Okay, so if we compute this, then what do we get? So Fy Fy of the 3/8, right? So Fy of 3/8. So what was like the CDF for us, right? So CDF, remember, was y square, right? So we have not noted this down here. In the previous slide, we had noted it down, right? So it's like y square when y is between 0 and half, right? So indeed, y is between 1/4 and, yeah, so y is between 1/4 and like 3/8, right? So 3/8 is within half actually, right? So in this case, it will follow y square, right? So we know that what we can do is y square. So y square is like 3/8 square, right? Minus, and 1/4 is again lying between that range, right? So this is again y square form. So 1/4 square, and the point Fy at like exactly just at 1/4, right? So Fy y at 1/4. Look, y at 1/4, right? And this is in the continuous case, right? So this is in the region of the continuous part. So it's going to be 0. Or is it? Yeah, so y Fy equals to so probability that, we are talking about probability, not Fy, okay? So probability that y equals to 1/4. Okay, so probability that y equal to 1/4. How do we retrieve this, right? So what do you think will be the probability that y is equal to 1/4? So this will be given by the discrete case, right? So discrete case, if we read it, because in the continuous case, remember, pointwise values doesn't make sense, right? So if you read out from the continuous case, that will be invalid. Okay, so when you are computing the pointwise values, the probability value, you should look up always in the discrete case to refer to, okay, whether there was a jump, something that I'm missing or something. Okay, so it is not a good idea to retrieve probability that y equal to 4 from the continuous case, because continuous case point values are taken as 0. Okay, and we are talking CDF makes sense, okay, but PDF doesn't make sense. So these are the things that one should be careful about. This is not Fy, this is probability. Okay, remember, this is a mistake here, right? So that's the end point that I'm going to add here. If it was Fy, then okay, you can think that will be cumulative. Cumulative will be contributed by continuous, discrete, but this must be referred, okay, from the discrete case only. Okay, so if I look back at the probability of y 1/4, right? Y 1/4 I will look up in the discrete case. Y 1/4, it is 0 actually. Okay, so I will put this remark here. So this is 0. So remark for probability y 1/4, we look into dy. Okay, because these are the discrete values, right? So we look up to dy and not in the cy, because cy, as I said, continuous by default, it's 0. So these are the small things that you have to be careful about. Okay, in this case, it turned out to be 0, so it seems like there was no contribution anyway. Okay, now let us, so this was the A part, and the B part of the question was find the probability that y is greater than or equal to 1/4. So probability that y is greater than equal to 1/4. So this is 1 minus probability that y is less than 1/4. Okay, so this is like 1 minus fy of fy of 1/4. Okay. So fy of 1/4 is how much? So sorry that I have to refer back again and again. So fy of 1/4 is actually 1/4 only, right? So in this case, like there was nothing, right? So fy is 1/4, so 1 minus 1/4 squared. So this is like 15/16. Okay. Look, here there is not even an equality here, so I don't even need to add back anything. Okay, basically because this is like a, I mean, this is how like this is defined anyway, right? Yeah, let's like write down again. So, so if we have this y less than equal to, let us say a, then this will be probability that y is less than a. Sorry, f y plus probability that y is equal to a. Okay, so we must add back the discrete part, right? I think we have to remember it correctly, right? So what was the like probability? How was this? So how was this defined? Recall. How was fy? I mean, if I say I should write a, right? So how was fy defined? That is the important thing here, right? So fy was defined as, was it defined as less or less than equal to? If it was less than equal to, then if it was less than, then you don't, but actually it was less than or equal to, right? So we may have to change few things here. Let us remember fy of a is probability that y is less than or equal to a, right? Right. So this is why it was defined, right? So equality was assumed in the definition of y, fya, right? Okay. So equality is assumed, and so to get the non-equality part, like I have to like subtract here, right? So here what we have is like less, right? Here we have is less. So we have to actually subtract back, right? We have to subtract back. So I hope you see this. So this is not really fy. Okay, fy less than a. So I can write this as what? So assuming that it's like a discrete case and so on, right? So this is like probability, because assuming that it's a mixed case, right? So probability that y less than a, and then plus I add back y equals to a. Okay, so probability that y less than a will be fy a minus that, right? Okay, so let me make, do I have a space? No. Okay, so let me make some space here. This is important, right? So the boundary cases, in the mixed case, boundary cases is very crucial. Okay, so we should not, we should be a little bit careful in what we are trying to do at the boundary. Okay, so I have made some space so that we can clarify these things here. Okay, okay, so what I said is the following. We have defined fya to be probability that y less than equal to a. Now assuming it is a mixed, assuming a mixed random variable, because if it is not a mixed random variable, then y less than a equal to y less than equal to a is equal to, so it's like equality and inequality doesn't matter in the, but in the mixed random variable case, we have to like be a bit careful. So probability that, so I can write fy of a to be probability that y is less than a plus probability that y is equal to a. Okay, so need to be careful in discrete case. Okay, so this implies probability that y is less than a is fy a minus probability that y is equal to a. Okay, so with this in mind, now so let me remove this part. Okay, and then I have to recorrect this part way. Okay, here. Okay, so so here fy minus a and then plus, I mean minus of that. So minus minus will become plus, right? So this will be plus probability that y is equal to 1/4. Okay. Okay. So again, like this guy is anyway going to be 0 anyway, right? So this is like 1 minus 1/4 squared. So this is like 15 over 16, right? So 16 minus 1, so 15 over 16, right? So this is the, yeah, this is the answer for B, and answer for C is like find the expectation of y. So to find the expectation of y, we differentiate the, because expectation is, for expectation we need like the PDF, right? So PDF we know, right? So PDF of the continuous part. So the PDF of the continuous part is dcy, like we are doing it again. We have seen this before. So this is like 2y and 0 less than equal to y less than equal to half. And it is 0 anyway, otherwise. All right. So now we can find the expectation because PMF we know for the discrete part, right? So only this PDF was needed, right? So expectation of y will be, so the range of y for the continuous case, it takes non-zero values. The PDF takes non-zero value only in 0 and half. So we have seen this before. So this is y times 2y dy. Okay, and plus, and then we have to put the expectation for the discrete part. Discrete part was, so it's like discrete part was defined at half only, right? So remember at half and probability that y is equal to half. At other places it was 0 anyway, right? And at this it was like 3/4, right? So this integration is y square, right? So y3 2 y3 by 3, right? So this is 3 and this is y cube. So y cube 1/8, right? 1/8 plus 3/4 was the discrete value at half. I mean 3/4 was discrete value of half, and then we have another half, right? So this is like 2 4. Okay, so it's like 12, 1 by 12 plus 3 by 8. Okay, 1 by 12 plus 3 by 8, which will be 12 and no, okay, so 24 and okay, and then 11, right? So 11 by 24. Okay, so this is how we compute the expectation, right, of the mixed random variable. Okay, so this is the example that I wanted to do just to be like sure that we have completed all three, right? Okay, so that's done. Okay. There are some solved problems. I leave it up to you. Like this is a question. I leave it up to you, I think. So what is asking for? Discrete, is this discrete? Because your CDF is given. So now you can immediately see if there is a jump or not, right? At X, it is approaching 1, right? So as X is At 0, it is like half. And so there is the jump, right? At 0, there is a jump. Right. So this is like x plus 1 by 2. And then you have 1 and then 0. So if you put 0 here, then it is half. So at 0, there is a, okay, so the bold will be here. Okay, so this bold thing will be here, and this will be a circle here. Right? For this part, there is these values, and from here onward, it's working like a linear function, and then for 1 onwards, it's 1. Okay, so that's the one part. So that's the plot. So there is a jump at x equals to 0. So this implies x is so it's some part it's continuous, some part is discrete, so it's like a mixed type. Okay, so this is an example of a mixed random variable. So I would leave this for the moment, the remaining part, and then you can try. Okay, you can try like find the PDF of x, right? So PDF is like the differentiation of the CDF. So you do this differentiation, it's not a big deal, right? And find the exponential expectation of the e to the x, like the function of the random variable. Okay, so I leave this up to you to do this. Okay, and then some conditional probability is given here, and all this you try as an exercise. I will put this in the assignment, and then if in case you cannot do, then you can get the answer in the tutorial, I guess, right? So that was the okay, and this is another example. Is it worth doing? So x is uniform, continuous random variable, and g of x is a new random variable y, whose PDF is given like that because it says, yeah. No, I mean, not PDF, is the function itself is y is defined like this. And now the question is like find the CDF of y. Okay. So how do we proceed this, right? So we are supposed to find the CDF of y, right? And x is a uniform. Okay, uniform and continuous uniform, right? So the PDF you know, right? So uniform AB is 1 by like B minus A or something, right? So how do we like go ahead and find the CDF of y, right? So first of all would be like to, it was good to find the range of y, right? So x, because whenever you are given function of random variable, you should keep track of the range, because these ranges will give you the range of integration that you have to bother about. Other things you don't care, right? So range, let us find out, right? So the range of y is between 0 and 1 only, because below 0, it's this is like x less than 0. So that's where the random variable won't contribute anything. Okay, so I mean not contribute anything. I mean the value of the, I mean the random variable itself is like defined to be 0 there. Okay, so the range of y will be, so let us do this. Yeah, here only. Then we can move to range of y will be 0 and 1. Okay. And I mean, these are the possible values that the y takes. Okay, it's 0, and the maximum bound it takes is 1 y, right? Because that's the one upper bound and the lower bound is 0. So that's the range of y that is defined. And from here, from looking at the range, we get the boundary values of the CDF. Remember? So now we get the boundary value. F of 0 is supposed to be 0 because y is below the range. And the CDF value at 1 is going to be 1 because that was the upper bound, right? So so these are the boundary values we immediately get by looking at the range. Now what we are supposed to find is something in between 0 and 1. That's the part of the CDF that is left to find, right? So this case is done. Let us do the remaining part here. So for y, for 0 less than y less than 1. So this is the part where we are left, right? So f y, let us find out. So this is by definition, this is probability that y is less than equal to y. E is equal to probability that x. So y is equal to x in this domain, right? So that's why I substitute y to be x, because y is given to be in 0 and 1. So y is equal to x and equal to y. So I fall back on y now. Now this is nothing but CDF of x and computed on y. And okay, and then so what is like the so what is this value now, right? So we are given that x is uniform, right? So if x is uniform, right? So recall the uniform distribution, right? So x is, and what was the range given here? -2 to 2, right? So let us not bother about -2 to 2. Let us recall just uniform AB, right? So the PDF of this was PDF of this, remember, for the uniform was 1 by b minus a for a less than equal to x less than equal to b. That's why it's called uniform. It's taking the constant value all the time, right? And this was defined to be 0 for x less than a or x greater than b. Okay, so this is how the PDF is defined. And since we want to do fx here, we are supposed to do the like the we are supposed to do the integration, right? So we are supposed to do the integration of the PDF of the uniform, because that's the uniform distribution x here, right? Okay, so let us try to do that, right? So yeah, so so what is this value, right? 1 by b minus a, we have to integrate it, and we have to integrate it from the range of x now, right? So from the range of x is -2 to 2, right? Because that's the uniform, right? So -2 to 2, okay? Because we are dealing with x now, right? So now I'm talking about range of x. We have to integrate over there, right? So this is like -2, okay? -2 to y, right? Because that's how the this is defined, right? So remember, f x of a is defined to be -infinity to a small f x dx, right? That's how the CDF is defined. In our case, a is y, and -infinity to 0, it was -infinity to -2. There was a range, there was not there anyway, so those values are considered to be 0. So that's why we started from -2 to y. Okay, and then the PDF of x is 1 by b minus a. In our case, a is this and b is this. So b minus a is 1/4, right? So 1/4 dx. Okay, dx or dt. Okay, it doesn't matter. You should not confuse with x. Okay, and this is how much, right? So this is like 1/4, and this is x, and evaluated on -2 to y, right? So this is like 1/4. And this is like y minus 1 minus 2, this is y plus 2. Okay, so this is the CDF that we found. Okay, and so what else we need, right? So if we have CDF defined for 0 and 1, but the point-wise values also we need, right? Because but the point-wise value is already known, right? Yeah, so we got the CDF overall, right? So CDF of y is now summarized, right? So summarize is like y less than 0, it's 0, and y, yeah, so let us write down, right? So y greater, and so I just write down here 1y plus 2 if y, let me like also include 0 because I mean, yeah, so let me include 0 because 0 is anyway not contributing. So I covered this case and this is 1 otherwise. Otherwise, in the case here, y greater than equal to 1. Okay. And yeah, so it is 0 otherwise. Otherwise is the case where like FYY is the CDF. Okay. So this is how like we found the CDF. Okay. Okay, what I will do next is joint probability mass functions. Okay. Yeah, so I will define something called a joint probability mass function. So what I will try to do now is we want to now look for joint probabilities. In other words, we want to look for things like x equals to x, y equals to y. Okay. So these are called joint probabilities where x and y are two random variables. Okay. So we are going into multiple random variable cases now. Okay. So let us see some definitions of these. So joint probability mass function of two random variable x and y is defined as follows. So this is how it is written for joint probability. This is the notation. Okay. This by this we mean this. Okay. So this is like probability that x equals to x event and probability that y and y equal to y event happens, right? So that's, and this case the joint range will be defined as all those x and y for which the probability values are positive. So that's okay. In other words, if range of x is x1, x2, let us say, I mean, these are, we are following the discrete case for the moment. Okay. So we can like enumerate these ranges and then we can also enumerate these y ranges. And we know that the range of xy will be subset of these. Okay. So that's like subset of the Cartesian product of the ranges. Also, we know that the sum of the joint probabilities must sum to 1. Okay, so if you sum up these joint probabilities should sum up. So that's like, again, I mean, you can think of these as like PMF of a joint distribution. Okay. So for any event A in R square, we have the probability that XY belongs to A will be set of all xi yj pair in A intersected with range of xy. Okay. And then you sum over the probabilities. Okay. So that's how you will compute the probability that xy is in A. Okay. So that's the way to compute probability. Now, there is something called marginal PMF. So computing individual probability from joint probabilities. How can we compute individual probability? So this is the joint is given to us, right? Now a reverse question is like, from joint, how can I get the individual probability? Let us say just px value or just py value, right? So that's why we have a concept of joint. So PMF of x can be obtained from the joint PMF as follows. So if you are supposed to find probability of only the x values, then this is equal to probability that x is equal to x. Then what you have to do is the following. Okay, so this is what we have to do. Remember what is happening here. X is equal to x is a fixed thing, but you are summing over all y equals to yj. Okay, so all yj in the range you have to sum up. Okay, over all yj. In other words, in the short form notation, we can write as pxy, and x is fixed. Okay, so this is like fixed guy. Of course, if someone gives you another x, then that will be fixed for that x. And then you have to sum over yj. So the important part is that you have to sum over the yj part. If you do this, then you will get the probability of x, okay, from the joint PMF. So we call this the marginal PMF of x, okay, because it's marginal. Okay, so it's computed from the joint in this way. Then px is called the marginal PMF of x. Similarly, we can define it for py. In the case of py, we sum over x. Sum over xi values. Okay, so that's like the PMF of y. Okay, so here y is fixed, but we are summing over the x. Okay, and you can do this for any fixed y in the valued range Ry. So that's how the marginal is defined. Now let x and y be two random variables with joint PMF as follows. So this is an example here right now. Okay, so x is equal to 0, x and y both jointly are given to you now. Okay, so if 0, 0 happens, then what is the probability? If 0, 1 happens, what is the probability? If 0, 2 happens, then what is the probability? And so on. Okay, so x and y be two random variables, joint PMF. In this case, it's discrete, so it can be tabulated. And if I plot it, then this is how the joint looks like. Now we are going into R2, right? So it's like if it is 0, 0, let us say, then it is like 1/6, okay, height. If it is 0, 1, 0, 1, yes, so x is this one, right? So x is 0, 1, so this is the point 0, 1. So 0, 1, the height will be 1/4. So this height is like 1/4 and so on. So we can plot it like this. Now it will look like a surface, right? Surface plot. In this case, discrete lattice, right? So so how do we compute probabilities in these cases, right? When we have joint joint PMF given to us, right? So another question is find the marginal PM of x and y. So from the joint, how can I get the marginal? How can I compute the conditionals? Okay, are x and y independent random variable? Okay, so these are the questions we have. So now let us answer the first question. The first question was probability that x equals to 0 and y less than equal to 1. So probability that x equal to 0, right? Okay, so equal to 0 and y is less than equal to 1. So this I can write this as probability that xy. So we remember we have to like probabilities are computed via like since this is a less than equal to here, y possibilities are y belongs to like 0, 1. X is fixed, so we have to vary y to 1 also, right? So probability x, y, and 0, 1 has to be added here. So this is 1/6 plus 1/4 is 5. So the 12 is the thing. Okay. And so this is the first one, and the second one is find the marginal PMF of x and y. Okay, so marginal PMF of x and y. So find PMF of x and PMF of y, that is the marginals. Okay, so remember to compute the marginals, we have to sum over the PMF, right? So you recall marginals, you have to sum over. So if I have to compute marginal of x, then sum over y. If I have to compute marginal of y, then I will sum over all x. Okay. So what is to be summed over? So first of all, let us recall what was the range of x and range of y. Range of x is 0 or 1. Range of y is 0, 1, 2. So range of x is 0, 1. Range of y is 0, 1, 2. So we have the marginal of x. And then like we have to define it for all x in the range, right? So x0 we have to first compute. So this will be the 0 will be fixed, right? So pxy 0 and then vary over all the y. So all the y will be 0 and 0, 1. Okay, not comma. And then plus probably that xy 0, x is always fixed, and 2 also because y goes up to 2. So we have summed over y. Okay. So here, so probabilities, if we read out 0, 0 is 1/6, 0, 1, and 1, 8. Basically, you have to sum over this. Sum this row to get px0, and similarly sum this to get px1. Okay, sum to get px1, right? So that's what we will do. So we have summed the first row, right? So if we sum the first row, then this is like 1/6 plus 1/4 plus 1/8 is something, right? And similarly, we have px1. So px1 will be sum of 181616. 181616. Okay. The third question is probability that y is 1 and x is 0 is probability that x is like 0 and y is 1 and probability that x is 0. So this is probability that we have 0, 1 divided by the marginal x is 0. So this can be computed, done, okay. And that the fourth one is x and y independent. Probability that, so let us compute some values. So for this to be independent, y1 and x equals to 0, let us pick some random values, right? So y1 and x equals to 0 is probably that x y 0 1 divided by probability x 0, and probability that x y so x 0 y 1, right? So x 0 and y 1 is 1/4, right? So it's like 1/4, and px0 was yeah, this guy. Okay, so 1/6 plus 1/4 plus 1/8. Is this equal to probability that y is equal to 1, right? So check this. Okay. Basically, you have to do this. So if they are equal, if they are equal, then try other conditionals. Okay. So recall, for this to be like independent, we have to do that y is equal to yi at x equal to xj must be equal to probability that y is equal to y for all ij. Okay. For x, y independent. Okay, so this is like one way to check. So it may not be that this example doesn't satisfy this. We have to prove, we are trying to disprove. If we cannot, we end up doing this, then they are like independent, right? If it so happens that it's not equal, then they are independent, not independent. So this is something like we have to check. Okay, so this is something you do this in the as an assignment. Okay, so it's an easy thing to check. I think with this I can stop. Okay, we will continue with multiple random variables in the coming classes. Like 3-4 classes will go into more than 3-4, because 7-8 classes might go into multiple, because multiple involves many things. Okay, sequences, vector of random variables, like it goes to many things, right? Central limit theorem, law of large numbers, the variety of things are there. So we will continue with this in the next class. Okay, thanks for your yeah, attendance, and then yeah, see you. Have a nice day.